Okay, so molarity is the unit for the concentration of something. So it is a unit. And to solve for the concentration of something, we take the moles of solute divided by our liters of total solution. So molarity, do you know what I mean when I say concentration? Okay, how much stuff is dissolved in there, right? So the unit that we are using to solve for concentration is molarity. And we solve for concentration with this equation. Okay,
Isn't concentration also based on like the solvent and if it can dissolve?
Yeah, it can. So it has to do with that. If it doesn't dissolve, then we won't be able to calculate a concentration, right? That won't work. But other ways that we could calculate concentration are parts per million. Have you heard that term before? Parts per million is like an environmental, usually used in like environmental science. So when you're talking about water quality and things like that, you measure in parts per million. That's one way. Another way that we can measure concentration. But usually we use molarity, which is big M. Okay?
Can you give the definition of concentration again?
So concentration is just how much stuff is dissolved in your liquid, basically. That's like a very basic definition for concentration, right? It's think about making Kool-Aid, right? That's the really simple example for concentration. If I put in 2 packets worth into 1 gallon, right, I'm going to have a higher concentration than if I make it as it's supposed to be made. Does that make sense? Or if I only use half a packet, it's only half as concentrated as it's supposed to be. That's what that we're looking at is. Okay? All right, very good. So I'm going to have to convert my milliliters to liters. That should be a quick conversion for us by now, I would like to think. Okay, so how can we convert milliliters to liters? Divide by 1,000. So move it 3. Okay, so we're going to divide that 97 mils by 1,000, right? 1,000 milliliters is equal to 1 liter. And so that gives me 0.097 liters. Okay, divide by 1,000. Go ahead and grab your calculator out if you don't have that. And you'll also need your periodic table. So let's go ahead and grab that out while you're looking for things as well. So I've converted my volume to liters. Can I use 1.24 grams?
No.
I have to convert to
Moles.
moles. Okay, and before I can even do that, I have to know what lithium hydroxide is, right? So I've got to be able to write out the formula for lithium hydroxide. Okay, so let's go ahead and get to that point that we can write out lithium hydroxide and figure out what that is. And then we'll convert to moles. Remember, hydroxide is a polyatomic ion. It's in the box, right? And it's one we memorized, maybe. Okay. So lithium is +1, hydroxide is -1, which means it's just going to go together LiOH. Did we all come to that conclusion? Yes. Okay, very good. So now we're going to convert 1.24 grams of LiOH, and we're going to take that to moles. All right, moles gets the 1. This is no mole ratio, anything like that. It's just a simple mole and gram conversion. So molar mass for lithium hydroxide, I don't know. Thank you. 24 grams. So 1.24 divided by 24 gives me 0.0517 moles. You don't have to necessarily take that many decimals. I don't know. I want to keep it as exact as we can. And that is 3 sig figs, right? Which is what I started with. So that works out okay. I'm going to take now to find my molarity, my moles divided by my liters. And that gives me 0.533. And then our unit that goes on the end is just a capital M, and it just stands for molar. So when we say it like this, as it's written as a concentration, we would pronounce that 0.533 molar, right? That's just how we would say that, how we'd speak that. I just rounded it there so that I would end up at 3 sig figs. Technically, I should really only have 2. I guess I'll take that away. 0.53 molar, right? So, not the end of the world, but that's what it looks like.
So do you care about sig figs?
No. I'm just going to kind of gently remind you every once in a while, okay? But not something that I'm really going to count off for, okay?
If we had something with 0.54.
Fine. Yeah, fine. Yep. Okay. Any questions? Does that feel a little bit more clear? All right, we're going to convert grams to moles. We're going to take moles divided by liters. It's, in all reality, a pretty simple calculation, right? We've just got to make sure that we do our conversion so that we've got both moles and liters. All right? Let's look now at a concentration of ions question. Okay. A 0.1025 gram sample of copper metal is dissolved in 35 mils of nitric acid to form copper ions. Then water is added to make a total volume of 200 mils. Calculate the molarity of copper ions. Okay. Calculate the molarity of copper ions. All right, so we've got a couple of different things we have to consider here. The first thing that we want to do is we know we're going to have to get this grams to moles at some point, right? There's no way that we can solve it with grams. So let's just go ahead and convert that grams to moles. So we're going to take 0.1025 grams of just copper, and we're going to convert that copper into moles. Okay, so the mass of it is the same. Right, molar mass of copper is the same whether it's +1 or +2.
Okay.
Yep. So 1 mole of copper, I think it's about 63.5. Okay, 63.5. I think it maybe has 2 5s. Either way, it's fine. So I'm going to go 0.125 divided by 63.5, and I get a value of 0.001614 moles. Okay, so that's moles of copper. Okay, so it tells me it gets put into a solution to dissolve it, right? To make it ionize. So that's just a little kind of side piece of information here. After that, it's added to water to make a total volume of 200 milliliters. So we dissolve it in nitric acid, that causes it to ionize. Then we dump that whole thing into water to have 200 milliliters of our solution. So we're not really concerned about the 35 at all, because the final volume of our system is 200 milliliters. Does that kind of make sense, right? The 35 mils was like part 1, but we don't really even care about that. All we care about really is our total final volume. Okay, so I'm going to calculate first the concentration of my whole system here, right? Concentration of my whole system, which is 0.001614 moles of copper divided by my total volume, which, can I leave it at 200?
No.
Has to be 0.200 liters. Bless you, 0.001614 divided by 0.2 gives me 0.00807 molar. It says calculate the concentration of all the ions present in 0.1 mole of calcium nitrate in 100 mils of solution. So we're going to calculate the ions present. Before we even do any calculations, I want to ask you what ions would be present here? If this separates, what ions would it separate into?
Calcium and nitrate.
It would become calcium. It would become calcium and has a +2 charge. And then how many nitrate ions would form?
2.
I would have 2 nitrate ions. Do you see how that works, right? When this separates, I've got 2 nitrate ions and 1 calcium ion. So when this separates, I will have twice as many nitrate ions as I will calcium ions. Do we see that ratio there? Right? Because there are 2 nitrate molecules per 1 full molecule there. 2 nitrate ions per molecule, 1 calcium ion per molecule. Okay, so let's look at calculating here. The first thing I want to do is I want to find the concentration of the whole system. And I do that by just taking 0.1 mole divided by 0.1 liter, right? And that gives me a concentration of 1 molar. Okay, and this would be for our whole system. Okay, so my full compound has a concentration of 1 molar. Now, what would the concentration of my calcium ions be? It would also be 1 molar because it's a 1-to-1 ratio. 1 calcium atom per molecule would mean that my concentration has to be identical. So my concentration of calcium ions would be equal to 1 molar. What about the concentration of my NO3 ions? It would be 2 molar, right? Because it is twice as much. There are twice as many nitrate ions per 100 milliliters as there are anything else, right? Because for every single molecule of this, there are 2 nitrate ions. So there are twice as many nitrate ions present in this solution.
So we're talking.
So first thing we're going to do is find the concentration of our total solution, and then we just compare the ratio, okay? So I'm going to take 2.5 moles over 1.25 liters. That gives me a concentration of 2, right? 2 molar. Okay. And so if this is the concentration of my total solution, what would my concentration of just sodium ions be?
2.
If my total compound has a 2 molar concentration, what would my concentration of just sodium be?
2.
It's going to be twice that much,
Oh.
right? So it's going to be 4 molar, right? Twice the amount, because for every molecule of sodium sulfate, there are 2 sodium atoms, right? So we have a concentration that is twice as much. So this would be 4 molar. Yes, Anna? This isn't concentration of ions. It's just a regular molarity problem. I think you should be able to do that one on your own. So let's try that. This is molar. So that's your concentration.
Rest of the chapter?
So dilutions are made from taking a really concentrated solution and essentially adding more solvent to it, right? And diluting it down. So we take, in our labs, what we do is we buy what's called stock solutions. And stock solutions are made in labs like to a really precise degree, right? They are made with a high level of exactness to be 2 molar or 10 molar or 18 molar or whatever. So I buy a bottle of that, right? And for my lab use. And so if I want to come to our lab and make one that's 0.25 molar so that I make sure it's not unsafe and whatever, but it still does what we need it to do, I can take my stock solution and I essentially water it down, right? But I've got to know some information to be able to water it down to the degree that I want it to, okay? So here's the equation that we use for dilutions. If we want to calculate or know how to make a solution a lesser concentration, we use this calculation right here. So C1 times V1 equals C2 times V2. What do you think those C and the V mean? Any idea? Concentration and volume, right? So this means concentration and these mean volume. Sometimes you might see it written as M1V1 equals M2V2, and this would just mean molarity times volume. Same thing, okay? I just was taught C1V1, C2, so that's the way I like to say it, right? But either way, it means the same thing, okay? The concentration of one of your solutions and the concentration of your second. So here's what I'll tell you. When we do these types of problems, you got to be really clear about your context clues in your problem, Okay, because you've got to make sure that you know which volume does this apply to. Does it apply to my stock solution or does it apply to my final goal volume and things like that? So we're going to be really, really careful and really precise when we read these problems to make sure we're really digging for context clues. Okay, so let's just go ahead and try one here. It says we need 500 milliliters of a 1 molar acetic acid solution from a 17.4 molar stock solution. What volume of stock solution is required? Okay. Now, when we set it up, we don't care if the stock solution's on the left and our final solution's on the right. It makes no difference. Left or right or equation, which way you put it, it doesn't matter as long as you don't mix and match them. Okay, so when I'm going to write this problem, I'm going to say, I know 500 mils of a 1 molar solution, that has to go together. That's my goal, right? I want 500 milliliters of a 1 molar solution. And then I also have a stock solution, and I want to know the volume of that stock solution. So those two parts have to go together, and these two parts have to go together. Bless you. So when I write out my equation, C1V1 equals C2V2, what I'm saying is that it doesn't matter if the stock solution is the one side or if the stock solution is the two side. It makes no difference, okay? I'm just going to write it out the way it's written, okay? So I need 500 milliliters of a 1 molar solution. I do want to go ahead and convert that to liters, okay? So 1 molar is my concentration, 0.5 liters is my volume. What's the concentration, the other concentration I'm given? 17.4 molar. And I'm solving for what volume I need to use of that concentration to get my final product. Okay, do we see how that gets set up? Then we just use algebra. That's it. So before we even do the algebra, I want you to think about what sort of number should we be expecting here? Should we need a lot of volume of that or a little volume of that? I think a little, right? I'm taking a really concentrated solution and I want to water it down. So I don't need very much of it, right? I'm going from really concentrated to not concentrated. So think about it. If I want to take, think about it in terms of color. So I take a bright red solution and I want to make it light pink, right? I don't need very much of that dark red, right? Only a little bit. Okay, so tell me what threshold do we have? My number could never be higher than what? My volume of here could not be higher than 0.5. I would never need more than that, right? That's my threshold. There's no way I should ever have more than my final volume here. Okay, so let's just go ahead and solve here. 0.5 divided by 17.4 gives me a volume of stock solution of 0.0287 liters. Or if you put it back to milliliters, would be 28.7 milliliters. Okay, I would take it in either liters or milliliters. It makes no difference. But do you see how I just need a small portion of that, right? Out of my 500 milliliter solution, only 27.8 milliliters of that is acetic acid. Everything else is water, right? And that's not even pure acetic acid. That's acetic acid at 17.4 molar, right? So even part of that's water. Okay.
Could you explain how you got V2 again, please?
How do I do the algebra for it?
Yeah.
I just multiply this side together, and then I divide that 17.4 over.
Okay.
Right? Because everything is multiplied.
Imagine if these are X.
Right. If I take 2...
0.5 equals 17.4x.
Okay.
So
Right.
you divide both sides by 17.4.
So I make the product on that side, and then I just get V2 by itself by dividing that to the other side.
Okay.
Okay?
I have a question.
Yeah.
So V2, that 2 isn't going to affect the answer. It's just
Yeah. That's just, you could say A and B if you wanted to. You know, you could label them initial and final. However you want to label them is up to you. Yeah. Yeah, you're right. The 2 makes no difference. Any subscript like that, right, it's not going to end up making a difference. But yeah, good question. It's not like a ratio like we see when we do ions. Okay? All right, let's try another one here, and then we'll almost be wrapped up, okay? What volume of a 16 molar sulfuric acid must be used to prepare 1.5 liters of a 0.1 molar sulfuric acid solution? Why don't you try this one on your own? Try this one on your own. It's very similar to the one we just did. The important part here is that we don't mix and match, right? We're not writing 0.1 molar with my unknown volume, and I'm not writing 16 molar with 1.5 mils, right? I don't want to mix and match those. I want to make sure I'm really consistent about what they need to be. So 0.1 times 1.5 divided by 16 gives me a volume of 0.009375. So that comes out to only about 9.4 milliliters, right? So a really small portion of my final volume is actually my acid, right? I need very little of that. So most of this 1.5 liter solution is water, right? Because only 0.009375 liters of that are even of our acid, right? Because 0.1 molar is a really weak concentration, right? It's mostly water. Okay? Tell me, what questions do we have with that?